Welcome to our 9th lecture of fax devices. Today we shall continue with the PWM techniques for the multi-level inverter. So, we were discussing on previous class with the level shifted PWM. So, what is level shifted PWM? The device, the basic features of the level shifted PWM is that the device switching frequency is obtained by multiplying the number of getting pulses per cycle by the frequency of the modulating wave. Moreover, the device switching frequency is not same for devices in a different bridge configuration. So, this is one of the disadvantage of it, the duty cycle of the actually RMS current rating and all those things will be different for the different switches of the H bridge. And output voltage of the H bridge, this H12 and H3 all are different, and in level shifted PWM the device switching frequency is not equal for the carrier frequency. So, this is advantageous or disadvantageous. If it is lower frequency, we can lower frequency and the higher current rating, we can choose a particular devices, and we can choose a, if there is a lower power rating and high frequency, we can choose a different current. There is an advantage, we can be used in an advantageous way also, even though it seems to be a disadvantageous. The inverter switching frequency equal to the carrier wave frequency, there is no change in that, and average device switching frequency will be given by actually FCR by M minus where M is the level of the inverter. Now, let us see that what happened in case of the side bands, and we can see that this is basically the neutral point or the phase voltage, and this is basically the line voltage, and it is been basically approximated by the ratio of VAN by VD. So, the dominating harmonics, it can be seen that VAN, that is a neutral voltage, and will appear in a side band centered around MF. So, you will get the THD and around of basically 18.6%, quite high PWM, quite high THD. And in this case, you will find that it is harbored around here, here, here. We have chosen the value of the MF in this case as 60. For example, if you are operating at a 50 kilohertz normal power supply frequency, 60 times is 3 kilowatts is your switching frequency. So, what happened here? The inverter phase voltage contains a triplet harmonic, though it will be not be reflected to your line harmonics, and such MF and such as MF, this is for this reason MF plus minus 6, with MF being a dominating harmonic, or the triplet harmonics are absent in the line voltage AB. It is quite clear. Now, what are the actually takeaway from this actually level shifted PWM? Conduction time of these devices are not continuous and it is distributed among the switches. So, thermal rating of these devices can be improved. So, we can use optimally their thermal rating. Switches, and so for this reason the second conclusion comes, switch devices and the average power handled by the each switch module are not evenly distributed. This is one of the disadvantage of it, and we require to manage as much as possible by the control logic, and it causes current distortion at the input side, that is not also advantageous, because you know that the MF plus minus 6 is present into the harmonic, and to evenly distributed switching and the conduction loss, the switching pattern should be rotated among the H bridge cell. That is something you require to manipulate with the with your control strategy. So, first of all you try to spend more amount of current through a particular H bridge, and maybe after 2 cycle later this sequence may change, and accordingly actually you will find that you will distribute the switching losses or the device rating among all the H bits connected in series. So, this is the sideband PWM with even power distribution. See that, please try to understand it. The problem of uneven power distributions in this line shifted PWM is solved by alternating phase shift carrier of each module, and the rotational levels are performed separately for positive as well as the negative carrier. See that here, this is the carrier wave. So, you can see that this is the zone where it hardly actually crosses. Ultimately, switching is mostly done on this part of it, and in this part also this is over modulation for this wave. So, there is no switching if it is continuously on for this duration. Similarly, in this duration it is continuously off. Same happened to the lower cycle. So, these can be something some way or other can be controlled. So, look, this is actually the point it is crosses, thereafter it will point, it will crosses something like. So, this is the carrier, this is the control signals for switch 1, this is for switch 2, this is for switch 3, and this is for switch 4. You can see that these carriers are basically crossing, but if you interchange in some half cycle, you give CR1 and CR2, then we can actually optimize the losses. See that what happened here. This is basically the V reference that required to be tracked, the modulating wave, and you will compare with the CR1, and ultimately you will have the CR prime, and accordingly when this value is V star or the V reference is more than this VCR delta, so switch S1 will be on. Similarly, switch S2 will be on when this reference voltage is greater than the VCR2. So, then subsequently other switches will be on. So, how you will generate it? A square wave signal for the half of the carrier frequency with appropriate amplitude to provide the offset and added to each carrier wave. So, you will add up, so it will be shifting positive and the negative half cycle accordingly. As the number of voltage level increases, the square wave signal has to be replaced by the staircase waveform, depending on the multi-level inverter. If it is more than 3 level, you require to be a staircase, and the output of the waveform will be same as that of the LS PWM, only H bridge output voltage will change. In that way, this is a simple way to implement LS PWM. Now, let us combine LS and PS, then what will happen? Then it is said to be the hybrid PWM, where you will find that basically there will be a mirror image form here. Actually, there is a phase opposition disposition. So, this and these are in a same phase, but they are phase shifted, but they are in the same phase, but they are shifted by the magnitude. So, hybrid phase shifted and the level shifted PWM are been when you combine the phase shift and the level shift, you get the hybrid one. Carriers are subjected to vertical as well as the horizontal sieve. So, see that this black line bolded and this black line dotted are the vertically shifted, and of course, you can see that they are also can be shifted, then it is a phase opposition. Only 2 bands are form the modulation. So, you automatically this actually the form. So, this so what happened in this case, the average device of the device switching frequency of the modulating hybrid modulation is half of the phase shifted PWM, and the dominating harmonic thus will be centered around m minus 1 by 2 into mf, where mf is the actually the modulating frequency index. The hybrid modulating frequency index with cascade multi-level inverter will have the following features. This technique involves both high frequency and the low frequency switching. High power modules are operated at a low frequency. To reduce the switching loss, we can choose a higher power device with reduced switching loss, where its switching frequency will be less, because you know that most of the cases are IGBT, IGBT having current trail. So, if the rating of the IGBT is more, then its switching frequency has been reduced. Low power module is controlled by the unipolar PWM. So, this is a very simplest way to implement it, what you have studied in the 2-level inverter. This method is only feasible if DC voltage of the higher power modules are the integer multiple of the small one. So, we have to, so if you put 40, another you require to put 80 and so on, something like that, and this kind of application is highly feasible in case of the solar inverter. Solar inverter, you can actually have a parallel, you can have a separate strings, and string size of the module can be changed by these equations, and thus it is actually a perfect fit with this control strategy. Moreover, this 3 module inverter having, this is the reasons V3 should be less than to V1 V2, and again V2 should be less than equal to 2 V1. In that way, actually we require to make this, consider this constraint to be satisfied. So, V3 should be greater than V2, it should be greater than V1. So, how you will do that? As I told you, in square wave you will have a actually steps kind of waveform. So, you will have a V3. So, from there you have a control logic, it is something hysteresis loop in x axis. So, you will then thus you will have a VA3, and VA3 actually will be subtracted from V3, and thus you get a VA2, and VA2 again will have a hysteresis loop in a control cell. Same way it will generate VA2, and again you will have this control cell, and ultimately you will get this VA1, and VAN will be summation of all the 3 voltages VA3, VA2 and VA1. If there are 3 power module, so this is the logic. So, plus minus H3 should be equal to VA1 plus VA2, and H2 should be equal to plus minus VA1, something like that. Now, see that hybrid PWM modulation. As we have discussed, the power output voltage VAN should be VA1, VA2 and VA3. So, see that this one is actually, this should be the ultimate modulation waveform, and this one is your VA3, and you require to generate also VA2, and this blue one is VA2, and this one is VA2. So, this difference of the steps kind of waveform is basically V2 minus VA3. Similarly, and you will find that there is a less ripple. Here power handling, this device will hold a maximum power handling, and this is the middleman in the road, and you can see that there is a ripple. So, it has to handle also the middle of the switching frequency. Same way VA1 you will find that it is different, thus it has to track this actually the error voltages and which will be high frequency. For this reason it is a low power device with the high frequency, it will be exactly fitting this application. So, thus ultimately you will get actually this kind of waveform in voltage and which can be eliminated with the help of actually low pass filter. Now, we have discussed different kind of PWM technique. Now, let us discuss the same PWM, same space vector modulation technique which we have discussed in case of PWM, in case of the 2 level, and we just extend it to the 3 level. We considered actually plus and minus there or 0 and 1 there, and here since actually we have 2 upper leg is short, then switch is short, we will say that this state as P. And when it is actually we have realized, please recall this actually this 3 level inverter with a triple throw single pole switch. So, when this switch is connected at this position and this is the midpoint of the capacitor and this is the point, when it is connected this position, then what happened? Then actually it is connected to the P. When this switch is connected this position, we say that it is connected to 0 or O position, and similarly when it is connected to the lower of the DC voltage, we will say that it is connected to the N. Now, since it has a 2 combinations, since there is a 2 switching combinations for a leg 1 and 0. So, there is a possibility of the 8 state 0 0 0 to 1 1 0 0 to 1 1. Now, in this case you will have actually 27 state. Now, among this state we shall see that few will generate the null vector and total 18 state will be there. And so, in that in case of the 2 level inverter for the SPWM, you know that actually 0 0 0 and 1 1 1 will give you the null vector. But here you will find many combination of it to generate null vector. So, you have a more redundancy with the switches and thus gives you more flexibility and the reliability. And what you require to do? We require to find out the relationship between the switching state and their corresponding space vectors. The same procedure we have used for the 2 level inverter. So, let us whatever we have discussed in the 2 level, same thing is applicable here. Based on their magnitude of the voltage vector can be divided into the 4 groups. One is 0 vector or null vector. So, these are basically when you 0 voltage is applied. So, this is actually all the upper switches is closed or all the middle switches are closed, that is 0 0 0, and all the lower switches are closed. Similarly, there will be small vector, these are V1 to V6 having magnitude, since you know that when we have talked about the decibels voltage, we talked about this actually total voltage is 2 by 3 VDC. So, in this case it is small vector or half vector, we will call it, then this value will be actually VDC by 3, and each have a small vector with 2 switching state, one containing plus P and another containing minus E, and therefore, can be further furnished into P or N times small vectors. Now, similarly, you have a medium vector, these are called half angle vectors sometimes, and we denote them from 1 to from 7 to 12, and whose magnitude will be actually VDC by 3, and it will be 30 degree, and there will be large vectors, and which was the present in case of the 2 level inverter also, and this will be present, and that value will be VDC by 3. If you only use this large vector, then actually then this 3 level inverter boils down to the 2 level inverter. So, let us see that we have calculated the time in case of the 2 level inverter. Can it be extended here? So, this is the dial clamp 3 level inverter, and this is the reference. So, see that P, that is positive, 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 when what is P? When S1 and S2 is closed for a leg. So, N, that is all the lower legs are closed, and 0, 0, 0. In 3 combinations, you will find that you are not applying any voltage to the line. So, it is null vector. So, this is said to be the V1. You can generate V1 with plus 0, 0, that means plus this and this, or you can also use 0 n. If you use plus 0, 0, you say that it is a P class of half vector, and if you generate by O n, we say that n class of half vector. Same way there will be a mirror image, it is OPP you can have, or you have n 0, 0, V1 and V4. So, see that these vectors, these half vectors can be generated. There is a 6 half vectors and we have of 12 combinations. So, you have a more amount of the flexibility, and considering that the phase VA, BC and till this 180 degree, actually you can see here from this point the phase A gets positive, till this time actually it lies positive. So, this is the basically the phase difference for positive phase or phase A. So, minus 60 degree to plus 60 degree. Similarly, you can see that for phase B, this P starts here and ends here, and here actually for phase C starts here as well as ends here. So, we can actually find it out where is the actually we can find it out the voltage V and theta. Let us say you are here and I have shown it is here. So, what happened here, you can think of that this voltage is made of V1, V7 and also V13. And what we require to do, actually since we can think of that this voltage it is required to you, and let us shift this origin here, and ultimately when you shift this origin here, so and you take this hexagon and you will find that this can be treated as a 2 level inverter, and same calculations what you have done for the 3 level inverter is valid. Same way for this leg also. So, thus let us take out that portion of the triangle and find it out what should be the value of the T1, T2 or in this case actually TA, TB, TS. So, dual time calculations for the neutral point clamp converter is based on the volt second balance. What we have done in case, same thing we have done in case of the 2 level inverter. The reference vector Vref can be synthesized by the nearest 3 stationary vectors. In this case we can see that it is with V1, it is applied for this time TA, with V2 which has been applied for the time TB, and Vc that is equal to Ts, and in between we had a null vector that will be there. So, we require to calculate same way the TA, TB, TC, and thus we require to know that for which time duration what will be applied. And you see that in between how it will work. So, when you apply PPP, so your load configuration is this. Similarly, when you apply P00, your load configuration is this. A phase is connected to positive of the DC bus voltage and it is connected to 0. Then you can also connect, and that will also give you 0, that is 0 NN. So, you get this voltage. Similarly, it is PON, then you get this kind of configuration, and PNN you get this kind of configuration. Now, you require to, I give it to an assignment, what you have done in case of the 3 level 2 level inverter to find out TA, TB, TC. I am not deriving here, and you are expected to derive and solve it for TA, TB, TC for the calculations. Okay, thank you. We shall continue with the next class, and this is our last lectures for the PWM technique. For next class onward, we shall start with the actually the fax devices, practical fax devices and its control and its applications. Thank you.